David. It should be.
All right. We need to cover up a lot of these things. What we have done so far, we did simple harmonic motion. We did damping of oscillations, right? And then we went on to resonance, and so you understand all the consequences of resonance. I think I demonstrated all those things. Good. And then talking about waves, I already classified waves as classified into mechanical and electromagnetic. Mechanical waves and electromagnetic waves. Now, what is the difference between those two? Mechanical waves, the medium is required, very important. Medium is required, and over there, medium is not required. The other thing about mechanical waves is mechanical waves will need a medium that is more elastic. The more elastic the medium is, the faster the waves can travel. Okay? Whereas electromagnetic waves, they travel best in vacuum, and they travel at the speed of 3 × 10⁸ meters per second. Electromagnetic waves travel at the speed of 3 × 10⁸ meters per second in vacuum, and they will actually travel slower when they go into some medium. So if they are actually going through water, or if they're going through glass, they will slow down. So electromagnetic waves. Now, what is an electromagnetic wave? Anything that is made up of electric and magnetic fields. So an electrical oscillation creates a magnetic field. So electrical field and magnetic field are right angles to each other. That's basically an electromagnetic wave. Now, what are the electromagnetic waves like? It starts from radio waves. Radio waves. What comes after radio waves is microwaves. And then what comes after microwaves is infrared. And what comes after infrared is a very narrow region, which is visible. Visible spectrum. And what comes after that is UV, ultraviolet. And what comes after that is X-rays. And what comes after that is gamma rays. That is the complete electromagnetic spectrum. So when you talk about radio waves, all the radio signals, the television signals, they're all radio. In terms of energy, got very little energy. Radio waves have very little energy. Right now, there are thousands of radio signals passing through your head. They don't really cause a problem because they are very little in energy. Gammas, big energy. So even one photon of gamma passes through you, it is definite to destroy a cell. So gamma is very energetic. X-rays, not as bad as gamma, but it still can damage. UV can cause cancer, right? Exposing yourself to the UV radiations can cause problems. So all these are energy types. And this one is the violet and this is the red. So this is the spectrum. There is violet, indigo, blue, green, yellow, orange, red. So that's the entire spectrum of visible light, the light that we see with our eyes. Right, Nick? So violet, indigo, blue, green, yellow, orange, red. This is the visible spectrum. And after this comes infrared. And after this comes microwaves and then radio waves. As I said, the application of radio waves used for communications and stuff like that. Microwave. What are the uses of microwaves?
Eating your food.
Eating your food. What else? What else? Microwaves are used for.
Heating.
Huh?
bacteria?
Killing bacteria? You're missing something very important. You use it on a daily basis, a minute-to-minute basis. Cell phones. Cell phone signals are waves. So microwaves, cell phone signals are microwaves. Now, in terms of which side of this is high energy? This side or this side?
The right side.
The right side is higher energy. So microwave oven and cell phones, where do you place them? Where is what? Microwave oven on the right and cell phones on this side, it is just the other way around. Microwaves, the cooking one is here and the cell phone signals are here. So the signal from the cell phones, they can cause heating. They can cause heating. In fact, they can cause cancer. Cell phones can cause cancer. That is the reason why we say cell phones can be bad. Now, you must have already sensed it. I'll tell you when. Imagine someone calls you, and then if the call goes on for 5-10 minutes, this whole section will become really heated up. You know, you can feel the warmth on one side. Have you not felt it? You really become tired and irritated. You don't like to continue the talk, but the other person is not dropping the call. So you just, you want the other person to stop because it's just like it's warming up this entire place. And what do you do instead? Switch it to the other side and start cooking on this side also. So microwaves can cause now. If you continue to do this regularly, you are disturbing cells, you are torturing cells. And the cells, when it's tortured, now they get damaged, but our body has a mechanism of making it up again, but you can't just expect the body to always make it up the right way, and eventually it can turn cancerous, and then that is cancer. So, can cell phones cause cancer? Yes, definitely. Now, the best way to avoid it is don't call for a long time. Cell phones are meant for emergency purposes only. And now the whole thing has changed. But cell phone's main purpose is just emergency. You call, all right, I got the message. No, that's it. If you want to continue to call, use a landline. That's a magnetic thing, that's okay. Or use earphones. Use earphones, but you got to have your cell phone next to you, so that means that's also bad. And keeping it in your pocket like that, that's terribly bad. Keeping it close to your body is bad. So if you're going to keep your cell phone far away and then have some kind of method of receiving the calls, then yeah, so cell phones can cause problems there. Microwaves, the microwave oven uses a different feature. That's why it is getting heated up. So the main purpose over there is to heat up, and that's why it is done well at this frequency. Infrared, where is infrared used? What is infrared used for? Say it again.
Thermal imaging.
To read barcodes, he said the infrared can be used. Scanners, cameras, infrared can be used in those things. In your remote controls, infrared is used in your remote control. So when you're pressing the button, what goes from your remote control onto the television is infrared. It's not that bad. It's not that bad, so it's all right. Infrared is the signal that goes from your remote control to the television. So when you're pressing the buttons on a remote, when you press the button on a remote, any button on a remote, it's supposed to give infrared. Can you see? Can you see anything coming out from here? You can't see it, but this camera sees it. I'll show you. Yeah, so the infrared uses are there. Infrared is also used for heat therapies, like physiotherapy. You can use infrared because it produces heat and it kind of stimulates the muscles and stuff like that. Visible light, of course, is the one which you normally use your eyes for. Ultraviolet. Ultraviolet light is used for killing bacteria and all those things, and that's also one application. Of course, tanning beds. Tanning bed is a place where you actually go pay money and then buy cancer. Yeah, that is a special place where you actually pay money to invite cancer. Because what exactly happening in a tanning bed? When you sit in a tanning bed, your cells are dying. And when cells die, it becomes dark. And so you say, I changed my color. It's a dead cell. So when you go to Florida or somewhere, spring break, and you just expose yourself to extreme sunlight contains UV. And that UV is what actually is destroying your cells. And because cells are destroyed, especially at the places where it's exposed, you see the tanning effect. And some people are very proud of the tanning effect. But after 1 or 2 weeks, the tanning goes off, right? That's because our body has a natural mechanism of repairing it. But you cannot just torture the body like that all the time. So people who regularly get exposed to sunlight like that, make frequent spring break visits and all that, as they grow older, they'll start getting skin cancer. There's no doubt those skin cancers are caused by overexposure, repeated exposure to sunlight. So I'm not saying like you just stand in sunlight and for some time you're going to get cancer. No, not at all. It is repetition. If you repeatedly torture one part of the body, then it causes cancer. Like smoking also. Like you repeatedly smoke, cause problems to the organs, and then again and again repeat it. The body can repair as much, but after that eventually it will give up. Same with alcohol. So just smoking one day and after that not smoking at all, it's not going to do anything at all. A little bit of, it's not going to matter, but of course it becomes a habit later on. Alright, so X-rays, where they are applied. Gamma rays, in chemotherapy and all that is gamma rays. And of course for scientific studies we have X-ray spectrometers, X-ray spectrography, gamma studies, diffraction studies. So there are a lot of studies that this section uses. So this entire thing is called electromagnetic spectrum. Now which one travels fastest, radio or gamma? They're all same. They all travel at the same speed as the speed of light right there. There's no difference. They all travel at the same speed. Okay, so that is about electromagnetic waves. Now coming back to this, mechanical waves. Mechanical waves are classified into two: transverse and longitudinal. Transverse and longitudinal waves. Alright, mechanical waves. Mechanical waves are classified into two major classifications. It's called transverse and the other one is called longitudinal. So mechanical waves can be classified as either being transverse or longitudinal depending upon how they propagate, how they move. Now what is a transverse wave? Why is it called a transverse wave? It's because it all depends on the particles. If the particles are moving up and down while the energy goes forward, like if you take a rope, and if I make the first part of the rope go up and down, which way is the energy going?
Up and down.
The energy goes this way, right? What's happening to the particles? The particles are jumping up and down.
You show that
Yeah. So if I'm holding a rope and if I just do the up and down movement like this, each particle is going to go up and down and you can see the wave moving, right? That is transverse. So what is transverse? Particle oscillations are perpendicular to the energy direction. You can write it down. Particle oscillations are perpendicular to the energy direction. The particles oscillate perpendicular to the energy direction. That is called a transverse wave. A longitudinal wave is when particles oscillate parallel when the particles oscillate like this, back and forth, then it causes longitudinal waves. And when it causes longitudinal waves, it forms places where there is compression, compression, compression. So it forms compressions. And then expansion, expansion. So you see this expansion. When particles move away from each other, it causes expansion. When the particles crowd towards each other, it forms a compression. So it forms compressions and expansions. So which way are the particles moving? Back and forth. Which way is the energy going? That way. That's why we call them longitudinal waves. So in a longitudinal wave, the energy is going that way and the particles are moving that way.
So the particles oscillate
Parallel to the directional wave, yes. The particles oscillate parallel to the direction of the waves. And here the particles oscillate perpendicular to the direction of the waves. So that's called a longitudinal wave. Huh? Anybody just hold it like this. Go back.
All the way?
Okay, it's fine. Now, just to demonstrate a transverse wave, what would be a transverse wave like? You know, if I'm going to hold this particle and move it up and down like that, you saw how the energy is going that way? You saw the energy going, right? And which way are the particles actually moving? They're moving up and down. This slinky is still here. Slinky is not moving. So the slinky's job is to go up and down. So when I create a wave, the wave is, now it's bouncing back from there. That's a different thing. Imagine he was not there, he was like far away. What can you see on the slinky is like this thing moving all the way. So if I create the waves, it will go all the way. That is a transverse wave. That is a transverse wave. You get it? Now longitudinal wave, particles are moving back and forth. Now I'll show you how particles move back and forth. So I'm creating a compression. See, I created a compression. And when I release the compression, you can see the compression. Okay, it's just bouncing back. Imagine there's no bounce back. It just keeps going. So the compression will keep traveling. That is a longitudinal wave.
You do both.
Yeah, you can do both. Like if there's a vibration like this at the same time it is doing that, yeah, in this it can be possible. Yeah. So, you understand what is longitudinal waves? Oscillations are parallel to the wave direction. Transverse wave. Now, what is a transverse wave made up of? Here it's made up of compression and expansion. Here it's crests and troughs. T-R-O-U-G-H. Transverse waves are made up of crests and troughs. Crests and troughs. Whereas longitudinal waves are made up of compressions and expansions. You get it? Now, some people, instead of calling it crest, they call it hills and valleys. Hills and valleys. But most books use crest and trough. Some call it peak and valley. Peak and valley. So this is the most commonly used thing, crest and trough. Crests and troughs. So transverse waves are made up of crests and troughs. Now, transverse waves and longitudinal waves are both classified into two types. Both of these are classified further into two types. Progressive what does it mean? What is the word progressive? Means it is moving. So you can see the wave going. Progressive wave is a wave that is continuing to go. And the other one is standing. A standing wave is a wave that does not appear to be moving, it stays at rest. The wave doesn't appear to be moved, it just stands there. So you can have progressive standing. Come back again. This. Together. Clamp it.
Clamp that right there.
Like that. Yes.
Understand.
Using your brain.
Okay, so you just have to keep holding it. Now, progressive wave is already, I already showed you this. Progressive wave is when the wave goes straight. Now, what is a standing wave? A standing wave is actually caused when a progressive wave going this way meets another progressive wave coming backward, and it sets up a standing wave. Now, in this case, I can just depend on the reflected wave and my ongoing wave. So, my ongoing wave and the reflected wave, they will create a standing effect. And you can see how the standing effect is seen. Come closer. Okay. So you can see how the standing effect is seen. Yeah, that is standing wave. Because this one is not appearing to be moving anywhere. Can you see this one? This part of the slinky is not moving at all. It's still. I can hold it. And then it is still. So that is a standing wave. This part is not moving. And I can create a standing wave in a different way. Depends upon the frequency. Look, this is also standing wave. That's also standing wave. It doesn't appear to be moving anywhere, right? Does it appear to be moving left or right? Now, that's a standing wave. Or I can create standing waves with multiple things. Yeah. There's a standing wave. See, this part is not moving at all. Can you see this one here? What I'm pointing out? It is always there, whereas the other ones are moving really wild. That's a standing wave. Okay. Ready. So a standing wave. So how many different kinds of waves are there? How many different kinds? How many different kinds of waves are there? You have progressive transverse, you have progressive longitudinal, you have standing transverse, and you have standing longitudinal. There are 4 types. So any wave that you kind of come up with should be one of the 4. Progressive transverse, progressive longitudinal, standing and transverse, and stationary and longitudinal.
What would standing longitudinal?
We're going to see all of them. Can you give an example of a progressive wave which is transverse? Any example? I'll give an example of a wave that is progressing, means moving from place to place, and it is transverse. Yeah. Sound. Yep. Waves on water. Like if you drop a stone into water, you know the ripples that are formed. It is moving from place to place, and it is a transverse wave. It goes like that. So waves on water, transverse. Or waves on a rope, transverse. Progressive and longitudinal. It should be moving from place to place, but it should be longitudinal type. Example. No, other than Slinky, anything else. Slinky is just a demo. Any other example of progressive and longitudinal wave?
Slingshot.
Slingshot is not a wave. Yes.
Like those little paddle boards, like with the ball at the end.
But that's not a wave. Why would you call it a wave? I'm talking about a real wave where energy is moving from place to place. Sound! If you're hearing my sound, that is Progressive because it's coming from me to you. And it is what kind? Which way the particles are oscillating? Back and forth, like this. So all sound waves are progressive and longitudinal. Sound through anything, whether it's sound through water or sound through steel or sound through air, it's progressive and longitudinal. Okay? Stationary and transverse. Where have you seen something moving like that? Stationary. Huh?
Jumper. Ridge.
Guitar string. When you pluck the guitar string, what you see is a standing wave. So all stringed instruments, guitar string. When you pluck the string, be it a piano or a violin, it's going to be standing wave, transverse. Yes?
Can you think of like maybe like a boat in harbor? Because the waves are constantly like the center boats just
The boat kind of goes like this. Yeah, it is a kind of standing effect. Standing and longitudinal. It should be longitudinal wave and it should be standing. A standing wave doesn't move from place to place, but it is longitudinal. What I showed you earlier. What is exactly happening over here? The sound that goes from the top and the vibration that goes on the top, it sends the waves down and then the reflected one comes back and sets up a standing wave right there. So because it is setting up a standing wave in resonance with the length of this tube, it is able to cause higher amplitude, and that's what you're hearing as a sound. So all wind instruments, like flute, clarinet, trumpet, church organ pipes,
saxophone.
everything, all wind instruments, standing waves and longitudinal waves. So whistles and all those things, everything is standing waves and longitudinal. Now, what kind of these are the four types. Which kind is this? Which kind is light? It is one of these.
PL.
Progressive transverse.
Is it progressive or standing?
Progressive.
It is standing. Is it transverse or longitudinal? It is transverse. You're just getting it wrong. Okay. So standing wave and transverse wave. It's a standing wave. Why? Because electric fields and magnetic fields are going like that. Electric field is varying like this and magnetic field is going this way. That's why it's standing. It's not moving. Transverse. That's why it's transverse. Standing. Why is it standing? Because it's a field. It is not something that's really moving. Light does not travel. Light does not really travel from place to place. Light is set up. It is made present. You know what I'm saying? It's not something like me talking to you. When I talk to you, there is definitely a wave that is traveling, and when it reaches you, you heard it. Whereas light is different. Light is when you turn on the lights, light just becomes present. How fast it becomes present is at that speed. It's like this. If I bring a magnet and keep it here, the magnetic field is set up at what speed? At that speed. It's not something that is like you bring a magnet, it's not something that starts from the magnet and goes on to wherever. No. So in fact, calling this a speed of light is wrong. The right thing to do is light is set up at that speed or established at that speed. That's the right way of saying it. Okay, so electromagnetic waves are all standing waves and transverse waves, be it radio or gamma. They're all standing waves and transverse waves. Any questions on this? Yes.
I still don't get how light is not.
So that is a transverse wave. This is a crest, and that's a trough. Crest. Trough. What is actually making up this wave are particles. So the particles are getting tossed up and down like that. Particles are getting tossed up and down. And that is how a wave is created. Now look at this model. Imagine this yellow strip is basically a rope. And each yellow thing, Lucas, each yellow thing is like a particle, right, off the rope. So when I oscillate, when I take the first particle and move it up and down, because all the particles of the rope are connected, each one will pass on the energy to the next one. So this is what you end up seeing if I create a wave. Say that. What is the job of each particle? Each particle's job is to really bob up and down and back again, but the energy is going through. So if I create a wave like that, you can see the wave is moving in one direction, right? Jose? Energy is moving. How can you when all this is going on? All right. So again, I'm moving it up and down, and the waves are going forward. You see it? So what is happening as each particle is bobbing up and down, and the energy is going forward. So as each particle goes up and down, you need to know certain things such as amplitude. What is amplitude defined as in a wave? It is a maximum displacement of each particle. It's a maximum displacement of each particle. That's what amplitude stands for. Amplitude stands for maximum disturbance, maximum displacement of each particle. That is amplitude. Time period. What is time period T? Time taken for each particle to move once up and down. Time taken for each particle to oscillate once completely. That is time period. And that of course tells you what is frequency. What is frequency? What's frequency? The number of times the particles oscillate in. Number of times particles oscillate in 1 second. That's called frequency. Now comes wavelength. Wavelength, the symbol that is used is called lambda. It's a Greek letter. Lambda. So wavelength, have you seen this wavelength before? The symbol? So lambda is a wavelength. What is this wavelength? It is the distance traveled by wave in one time period. In one time period, how far can it go? That is called the wavelength. Which means what? Which means when I take the first particle and oscillate it up, down, and back, that's one time period, right? Right? If I take the first particle and make it go up, down, and back, I finish one oscillation. That is one time period. In that period of time, where did the energy go to? That is called the wavelength. In other words, if I'm going to oscillate this once up, down, and back, the energy would have gone till here. So that is the wavelength. So this is one wave back. That's one wave. And that will be our second wave. So what is exactly wavelength? Wavelength is the distance from one crest to the other crest, or from one trough to the next trough, or from one point to another identical point. That's a wavelength. And it's measured in meters. Frequency is measured in hertz, time period is measured in seconds, amplitude in meters. So you know all this. So what is lambda? Lambda is the distance moved in. So distance moved, time. Lambda is the distance moved in t seconds. Is that right? Is that right? Lambda is the distance moved in t seconds. Therefore, how far will it go in 1 second? How far will it go in 1 second? If it can travel lambda meters in t seconds, in 1 second, how far? One cake with $5. So for $1, what do you get? What you do there is the same thing what you do here. Lambda over t. You get it? Lambda meters, it travels in t seconds. And therefore in 1 second, you divide by t both sides. So it will travel lambda over t meters in what? In 1 second. The distance moved in 1 second, what is it defined as? What do you call that? Distance moved in 1 second? Frequency. Distance moved in 1 second? Come on. You did all the mechanics in the world and now you're saying it's velocity or speed. Right? The distance moved in 1 second is speed. So this is speed. So we have this important equation now. V is equal to lambda over t. But what is 1 over t? What is the reciprocal of time period? Frequency. Reciprocal of time period is frequency. So this equation becomes V is equal to frequency times lambda. This is a very important equation in waves. It's called the wave equation. The very basic wave equation is velocity is equal to frequency times lambda. Frequency. We can also call frequency. What is frequency? Number of times particle oscillates in 1 second. We can also say how many waves are generated per second. That's also frequency. How many waves are generated per second? Number of waves generated per second. That's also frequency. Number of waves you create per second, that's frequency. So velocity is equal to f lambda. And understand this, that frequency and lambda are inversely proportional. Frequency and lambda are inversely proportional. When the frequency goes up, the lambda goes down. When the frequency goes up, you can see that over here. When I am oscillating this with a low frequency like that, look at the lambda. When I oscillate this with a low frequency like that, see, you can see the crest to crest distance is big, right? The crest to crest distance is big when I do it slowly, see. The crest, can you see the crest to crest distance? Because it's moving, it's not easy to see. Alright, but when I do it faster, the crest to crest distance will be shorter. Look, it's only short. So the wavelength depends on the frequency, inversely. You get it? So the faster you oscillate, the wavelength is shorter. Like for example, when I'm speaking with a frequency of roughly 300, 400 hertz. My vocal cords are shaking with that frequency. Now imagine there's a lady teacher speaking with a higher frequency here. Speaking, whatever. Alright, so who will have a bigger wavelength? I will have a bigger wavelength. So my wavelength will be approximately this long. This is one wave of mine. And the lady should be possibly talking with a higher frequency. And when it's talking with a higher frequency, then the wavelength is shorter. So for the lady, the wavelength can be that much. Whereas in my case, it's so the deeper you, the lower the frequency, the higher the wavelength. You get it? It's inverse proportion. And this is the speed of sound. That will be the speed of sound. So whoever talks here in this room, the speed is going to be just 1. It's not affected by who is talking. Speed of sound depends on the medium. It depends only on the medium. Any questions here so far? Okay. Now that equation is true for any wave, whether it's electromagnetic. Okay, for electromagnetic waves, we don't write V equal to F lambda. Instead, we change the V to C. So we say C is equal to F lambda. The speed of light, we call it C. You must have heard of E equal to mc squared, C. Right? The C is for speed of light. So instead of reading this as V equal to F lambda, you can actually call it C is equal to F lambda. The speed of waves depends on the material medium. Like over here, when I'm talking, the speed depends on the air. The speed depends on the air itself. Speed of waves depends on the medium. Now, if you're sending transverse wave through a metal, if you're sending transverse waves through a metal like a guitar string, the speed is equal to radical tension over mass per unit length. That's how the speed is affected. The tighter you make the string, the waves go faster. Okay? So transverse waves going through a metal, the speed depends on tension. You tighten it up, it goes faster. And the other thing at the bottom is mass per unit length. What do you mean by mass per unit length? You know what is mass per volume? What is that? Mass per volume? Density. Now, mass per unit length is called a linear density. What it simply means is you take 1 meter of that metal and weigh it. That's mass per unit length. For 1 meter of the wire, how much does it weigh? That is mass per unit length. So if the mass per unit length is kind of a heavy thing, then the waves cannot go that fast. You get it? If it is a light material that you're using for transmission of energy, then it will go fast. So if I'm taking a string or a rope, and if I tighten it up like this and then send the waves, it will go really fast. If I loosen it up, it will go slow. You understand? It depends on the tension. Longitudinal waves through any medium. The speed depends on the modulus of elasticity and the other one is density. Now, modulus of elasticity is not in your syllabus requirement, but just understand that there is something called elastic modulus. Different materials have different modulus of elasticity, like steel has one, aluminum has another. They are all different in elasticity. Steel has got very good elastic modulus. So the speed of waves through any material, longitudinal waves, like sound waves, depends on what factors. Modulus of elasticity. What about air? The air has got very poor modulus of elasticity. It doesn't have much elasticity. That's why speed of sound in air is 340 meters per second. You get it? Whereas through steel has got a good elastic modulus. Even though steel has got more density, the modulus of elasticity is many-fold more. And that's why speed of longitudinal waves through steel is very high, and I think I told you 5,000 meters per second. It's pretty strong. So just keep that in mind. This is an equation that this is tension in newtons, and this is mass per unit length in kilogram per meter. Okay? And that is the speed of transverse waves through a string. So if I'm sending transverse waves, at what speed are they going here? Depends on the elasticity of the material that I'm using here and its density. Okay? So guitar string, for example. That's why different strings have different thicknesses, right? You have different strings of different thicknesses. So the thick strings will give you a low frequency, and the thin string gives you a higher frequency. And why they give low frequency and high frequency is because the speed is affected by the thickness. When it's a thick string, the speed is low. So you'll get a low frequency for the same segment of the string. And when you have a thin string, it's got higher velocity, so it's got higher frequency. You get it? We'll talk about that equation later on. So understand this equation that actually tells you the speed changes. Reflection of waves. Reflection of waves. Waves can get reflected. Waves can get reflected in two ways. So if I'm going to take a rope like this and send a crest like that, if I send a crest, and if I tie the rope at that end, that becomes a fixed boundary. Or I can also do this. I can send the pulse to a free boundary. That's a free boundary. So reflection can be from a fixed boundary or a free boundary. Now you know what's the difference between fixed and free. Fixed boundary, the rope is like tied up there. Whereas a free boundary, the rope is not held like that. So when the waves go there, this has the freedom of movement up and down. Understand what I'm saying? So when you don't tie it up somewhere, then it becomes a free boundary. So what exactly happens in this case? When this goes over there, when it comes back, this is how it comes back. The crest becomes a trough. The crest will change into a trough when it bounces back. Whereas in a free boundary, what happens? The crest will remain a crest. In a free boundary, the crest will come back as a crest. In a fixed boundary, the crest will come back as a trough. So what goes is a crest, what comes back is a trough. Those are the two kinds of reflections of waves. I'll demonstrate that here. I'm going to send a pulse wave from here, so watch this. And I'm going to send a pulse wave from here, a crest. I'm going to send a crest from here. And I want this a fixed boundary, so I'm holding it. I'm holding it, so it's a fixed boundary, right? So what should happen to the waves? The crest should go and bounce back as a trough. So just watch that. You can see the crest changing into a trough. There goes the crest, turned into a trough. You see it? Did you see it properly? Right, I'll do it again. I'm holding this firm and I'm creating a crest. There goes a crest, turned into a trough. Now what is the other one? The other one is reflection at a free boundary. No, that's free. I'm not touching it. So what should happen? The crest should go and come back as a crest. So I'm not touching that end, so it's free to move. And if I'm going to create a crest, the crest should come back as a crest. The crest bounces and comes back as a crest. You see it? That is how reflections take place at boundaries. Let me know if you have any questions at any point. The next concept is interference. What is the word interference? What does it mean normally? Getting in the way? Yeah, this is getting in the way of my notes. Interference. So what is interference? It is when something gets in the way. Like for example, I'm teaching and everyone's supposed to listen to my talk. Well, that is supposed to be the main goal. If somebody kind of starts talking in between, that is interference. Because what will happen is when someone starts talking, people are not going to listen to my speech alone. It will be a mixture of both, and that will mess things up. Right? You don't want to listen to two radio stations at the same time. It will be messy. And sometimes it happens when you tune to a certain station. You know, you start hearing that station, and occasionally the other station starts coming in. Right? Have you heard that? Kind of coming in together. That's interference. If unwanted signals come in, that is interference. Have you heard interference from a computer screen, a computer speaker? It starts chirping, especially when your cell phone is about to go off. Go on. Have you heard that? You should. The thing is, you should be very vigilant to anything that looks abnormal, and don't blame it on ghosts and stuff like that. You always have physics behind it. So if you are hearing a strange sound, immediately you should have that inquisitiveness. Immediately, why is that sound coming? Where is it coming from? Why? That's how you should be to learn stuff. And now these days it's so easy to get information. Look up your YouTube and find out. Oh, you have definitely seen this before or heard it before, but you just don't connect it. All right, type in computer speaker interference from cell phone and find out what happens. Computer speaker interference from cell phone. So, yeah, when the cell phones are about to go off, the signals are actually coming from the tower to your phones, and that is basically when the computer speakers pick up some stray signals and then they start chirping. That's interference. So, interference is when waves, two or more waves, come together. You get it? Like, for example, if I take a rope and if I make it go up and down like that, and if someone else is holding the same spot I'm holding and creating a new wave here, someone else is oscillating it like this, what will happen to the poor rope? It will not listen to my instruction, it will not listen to this instruction, it will take up a new position altogether. So it will create a new wave. It's something like this. If I'm telling Daniel, go to your left 2 places, he goes 2 places. He comes here. And imagine some other lady teacher is standing there and saying, Daniel, go to your left 1 place at the same time. So where is he going to settle down? Here. He will listen to me and listen to the other person. So eventually he's getting to a spot which is not either of our instructions. You get it? That is interference. That's interference. So what's happening over here on the rope? The red one, watch this. The red one is not doing anything here. Blue one is not doing anything, so the particle is right there. Okay? Now what's happening at this time? The red one is asking me to go here, but the blue one is asking me to go here. So where is it finally going to go? Up there. What about at this point? The red one is asking you to go there, and the blue one is not asking you to go anywhere, so it will be here. It will take the new position. You understand what I'm saying? What about at this point? It will be somewhere here. What about at this point? It will be somewhere here. and at this point it will be there, and then after that it keeps going like this. So eventually what will happen is the graph is going to, the rope is going to take new positions like this. So you get a totally new sort of a wave. Look at the wave shape. So the wave will be a complex wave, and that is because of what? Interference. That is called interference. Now interference can be sometimes constructive and sometimes can be destructive. There is constructive interference, destructive interference. Actually, what? Imagine you take a rope and send a crest from this rope, while your friend sends another crest from here. So basically it's the same rope. One sends a crest from here and the other sends a crest from there. So what will happen to those crests? They're going to move. After some time they're going to be there. What will happen after some more time? They both collide. What will happen at that point? They'll climb up more, and that's called constructive interference, because they are adding up. It's like one person telling Daniel, go to your right this place, and the other person saying, go 2 more places. So he ends up with a big amplitude. So this is constructive interference. And what happens eventually, the one which came from there will continue to go its way. The one which came from here will continue to go its way. Nothing is getting stopped. It's just like a passing through. So while it is passing through, you get a high amplitude. That's constructive. Obviously, the other one is destructive. Now, what is destructive interference? When I create a crest from here and a trough from here. If I create a trough from here, what will happen at this point? What will happen when they both merge? Destructive. What will happen here? Nothing. It will be almost straight, momentarily straight. And what happens immediately after that? The one which came from that side continues to go its way. This one goes. So basically what happens at this point is it's kind of stored in the form of elastic energy for a moment, but you don't see any amplitude. You don't see anything. That's called destructive. That's destructive interference. Destructive interference. And these things can be demonstrated here. I'll show you a real life demonstration and demonstration from here. Can you see one of them red color? Right? Watch the red one. I'm going to create 2 crests from both sides and see what happens to the red one as both the crests come there. Hopefully I'm counting 1, 2, 3. Okay. Watch the red one when I'm creating the 2 crests. So here goes the 2 crests. Did the red one get tossed more? Watch again. 2 crests. The red one is kind of tossed more than the others, and that is constructive. Now destructive. Destructive, I'm going to create a trough from one side and a crest from the other side, and let's see what happens. Now I have to create exact amplitudes in order to cancel off. So what should happen to the red one? It should not move. So when I'm going to create a crest from one side and trough from the other side like that, the red one literally stayed there. You see it? The red one did not move, it stayed there. And that is destructive interference. Now let me show you the same destructive interference in real life. As a frequency generator, I can create sounds. not the bell.
What the?
What?
Wait, can you do that again?
Now, that is the same frequency as the bell. So if I actually hook it up, remove the speakers, and give a parallel connection, it will ring everywhere.
Do it.
All right. So what I'm trying to show you is this. I have two speakers here. I've got two speakers. If I connect this to this speaker, if I'm connecting one of them to this speaker, I connected one speaker and it's perfectly sounding well. I'm connecting the other speaker. Now both are on. Both are on. And you don't find a big difference, right? They're both perfectly normal. Now what's happening over here is both of them are creating compressions at the same time. What if I flip these wires? One produces a compression when the other one produces an expansion. And see what happens if I connect the wires the other way. Where's the sound gone? Destructive interference. The sound is still there. The only thing is when they came like that, it's kind of killing the sound because of constructive and destructive. So you don't hear literally anything. But if I remove one of them, now only one is working. But when two of them work, they cause destructive interference. Voice cancellation, yes. That's the idea of voice cancellation. Noise cancellation, yes. So what happens is you're listening to your music. What the noise cancellation does is it picks up the noise, inverts it, and feeds it back again. So what happens is you hear the noise and the negative of the noise gone. That is destructive interference. Good? Good. Oh, why do we stop so early?
Just sound like the bell. Ring the bell for it. Yeah,
Ring the bell for you?
Ring it a minute early.
So is that the same speaker as like what our bells?
What's that?
Is that the same speaker as what our bells are?
No, not same frequency. I can change the frequency. I can change it. I think this is the bell. I've tried this when, like freshmen are about to go into the room, into Mr. Badniak's room, just 1 minute before the bell. Yeah, that's a real bell. Oh yeah, they start running. They start spinning into Mr. Badniak's room. Oh, it's still on? Yeah.